So let's consider the differential equation dy dt equal 2t. If we think about the solution, you could probably figure out what this is. What was the function whose derivative is 2t? And you may think of t squared. We're just thinking of antiderivatives, but hopefully you also remembered the plus a constant. So the solution to this differential equation, t squared plus c, this looks like a family then of solution curves that look similar to each other because they're all parabolas, but they have their vertical translates of each other depending on what our c value is. Now, if we defined a specific point, so at t equals 0, this function value was -2, then we could identify the curve. And as we look here, we can see it's kind of the magenta one. And then we would have a unique specific solution here and not the whole family of curves. When we are given a value like this, it's called an initial value problem. We give an initial value at t equals 0. This function value is -2. That's also abbreviated IVP, and that stands for initial value problem. So if you see in the directions to solve the IVP, you'd know what to do. So here we have a differential equation, and here we have a solution. Let's verify that it really is a solution. So what we would want to do is take the derivative, and that would be 1/2 c minus t squared to the -1/2 multiplied by the derivative of what's inside, which is -2t. Now what we're going to want to do then is substitute the derivative here and the function here, and then verify that they're really equal to each other. So this would actually cancel here, and let's go ahead then and do that substitution. So first we need the derivative, which is right here, so that's going to be -t over the square root of c minus t squared. And the question is, does that really equal, now I'm going to use this right hand side, -t over y, well y is right here, square root of c minus t squared. And in fact you can see that the left hand side equals the right hand side. So yes, this is a solution. Can you find the value of c so that the graph shown here is the graph of the solution? So right now, as we see this, this is a family of solution curves. So we want to find the specific family member that has this graph. So we could look right here and we could see that at 0, this equals 1. So what we would need to do is just simply take the solution, put in 0, and set that equal to 1, and then solve that to see what the c would need to be so that that would be the curve. Alright, so we can do that. That's just 0, and we would just square both sides. So c equals 1. So the solution would be square root of 1 minus t squared. Now, I did that officially. You could have probably looked at this and said, oh, it's a semicircle of radius 1, so the c has to be 1, but I wanted to show you the steps for solving that. So here's another example. We have a differential equation. We actually have a, quote, solution. We want to verify that that's true, and then we want to solve the initial value problem, IVP, because here is an initial value, and identify which of these curves it would be. So what we want to do is take the derivative here, which would be -c e to the -t plus 1, and then we're going to use this differential equation, substituting in each piece, and see if they're really equal. So the derivative was -c e to the -t plus 1, and the question is, does that equal t minus the solution, which was c e to the -t plus t minus 1. So as we look at that, we can see that if we distributed this through, that the t's would cancel, and we would be left here with -c e to the -t plus 1, and that is exactly what our other side is. So yes, this is a solution. So now we need to figure out what the c would be to have this as an initial value. So we would take this solution and figure out 0. So this would be c e to the 0, which is 1, plus 0 minus 1, and that needs to equal 3. So c would need to be 4. So the specific solution would be y of t equals 4e to the negative t plus t minus 1. So we could look here, and here's the one at 0. It is 3. For what value of k is y of t a solution? So what we want to do is find the derivative here, which would be k e to the kt, substitute in here, and figure out what k would need to be so that made a true statement. So we'd have k e to the kt plus, we need to substitute in our y, which is e to the kt, and that equals 0. We could see that would only equal 0 if k equaled negative 1.